Hey there, welcome to Geography. And in this video, we're going to look at Earth and Sun relations. And specifically, we're going to see how the Earth moves in relation to the Sun. And we're going to see how that creates different levels of incoming solar radiation at different places in the world based on where the Earth is at a given point in time. And then finally, we're going to look at how that creates our seasons. How do we get seasons from the different levels of solar radiation throughout the year? And also some special cases like midnight sun and polar night. How do those occur? And we'll see a few ways that the different points throughout the year and the seasons affect people. So the Earth spins on an axis that runs from the North Pole down to the South Pole. It's an imaginary line or stick that runs through the center of the Earth, from the North Pole all the way to the South Pole. And the Earth rotates or spins on that axis every day, one time. So one rotation per day. The direction that it rotates is important because it determines how the sun rises and sets. You may know that the sun rises in the east. That's because the Earth rotates from west to east, as you see on the diagram there. The way I remember that is that we read in that same direction from left to right. And so, because on most maps, west is on the left, and east is on the right, it's the same way, left to right. So the Earth rotates from west to east every day. And that's actually going to allow the sun to rise in the east and then set in the west as we rotate away from it. So one rotation takes 24 hours. In addition to the rotation, the Earth also revolves in an orbit around the sun, and that takes 365 and a quarter days. So every 4 years, we add up the 4 quarter days and we get one extra day. And that's a leap year with one extra day. So February 29th. So 365 and a quarter days is how long it takes for one revolution, one orbit of the Earth around the sun. Johannes Kepler, during the scientific revolution, figured out that the Earth's orbit is not a circle, it's a stretched out circle, which is an ellipse. An ellipse has two centers, two foci, here and here, as opposed to one center like a circle. And that elliptical shape is putting the Earth at one point in the orbit closer to the sun, which is called perihelion. Peri means around, and helios is the Greek word for sun god. And then aphelion is when the Earth is furthest away from the sun in its orbit. Now, this diagram is very much not to scale. The Earth is not that different in terms of its distance from the sun at perihelion and aphelion. They just exaggerated it to make it look like it's much farther away during aphelion. In reality, it's only a slight difference in distance from the sun. And to be clear, this is not the reason why we have winter and summer different seasons. It's not because of this distance. What keeps the Earth in orbit? What keeps the Earth from flying off into space? What keeps the Earth from falling into the sun? It's a balance of two forces. So in physics, we have centripetal force, which is the force of pulling in. And then we have centrifugal force, which is the force pulling away. And so in this case, you see on the left is a guy swinging a rock around. The centripetal force pulling in is his arm. The centrifugal force making the rock want to fly away is inertia, the fact that he's wound it up and swung it around and given it momentum and inertia. So those two forces are in balance until he lets go. And then the centripetal force is gone and the rock flies away because of centrifugal force. It's the same thing with the Earth in orbit. There's an inward force of the sun's gravity, centripetal force towards the center. But then there's also Earth's inertia from being in motion in orbit for so many millions of years. And that's pulling outwards. So that's centrifugal force. One way that I remember centrifugal force is that root word FUG, fugue. It's like a fugitive or a refugee. It's all the same root. It means something fleeing or going away. So centrifugal force is the force of fleeing, moving away from the center. And it's the balance between those two that keeps the Earth right in the orbit where it is. If the sun were to disappear for a moment, then the Earth would start flying off into space because of its inertia. If the sun's gravity were to increase, or if the Earth's inertia was to decrease, slow down a lot, for example, then it would start to fall into the sun. So it's sort of a magical balance that it has. Another amazing balance in the Earth is that the Earth is in what we call the Goldilocks zone, the livable zone where the temperature is just right to allow the water to be liquid. Remember the child story of Goldilocks and the Three Bears? There's a Goldilocks comes into a house and the three bears are not there. And there are three bowls of porridge. One is too hot, one is too cold, and one is just right. So the Goldilocks zone is just right for water to exist as liquid, because you need liquid water for life. You can have water as frozen ice in Mars, but there's no life on Mars. It's not the Goldilocks zone. There is frozen ice on Mars. And you could have Venus as well. You could have water there as perhaps steam somewhere in the atmosphere, but that's too hot to have liquid water. So Venus is too hot. It's the planet before Earth, closer to the sun, and Mars is the next one out, is too cold. But Earth is just right. It's the Goldilocks zone where water can be liquid. Therefore, you can have life. People speculate as to whether in the past Mars may have been able to have liquid water, in which case it may have had life. And some people speculate as to whether there could have been life on Mars. So to connect those ideas, the fact that Earth is in that balance of orbit between gravity, centripetal force, and the centrifugal force of inertia keeps it in that particular orbit, which puts it in that particular Goldilocks zone, which gives it the ability to have liquid water, which gives it the ability to have life. So it's all fitting together. Let's talk about the Earth's axis. Again, it's not an actual stick or something you could point to. It's just an imaginary line through the Earth around which the Earth spins, rotates. Earth's axis always maintains two properties that both start with P. One is polarity, and the other one is parallelism. Polarity and parallelism, they go together. The property of polarity means that Earth's axis, which you see in the picture there, the blue, always points to Polaris, the North Star. So you look in the picture, the Earth is going to go around its orbit, and it's always going to point to that same North Star. And you may be saying to yourself, well, how is that possible? When you see the Earth moving over here to the right on that orbit, it's going to not point to that North Star anymore. That's because the diagram is not drawn to scale. You can't draw it to scale because the North Star is so far away. The sun is extremely far, and then the North Star, Polaris, is thousands of times farther than that. So you would not be able to draw where the North Star is. But if we imagine it's super far away, then the Earth going around in the orbit and that arrow of the axis moving throughout the orbit is not going to make much difference because the direction of the North Star is so far away. It's still going to point towards that North Star. So that's polarity, the property that the Earth's axis always points toward the North Star. And there's actually also a southern star that the southern axis points to as well, called Sigma Octans. You see that in the picture as well. They say that sometime in the future, long, long in the future, the Earth axis will point to some other star, but that's not in our lifetime. The second property that starts with P of the Earth's axis is parallelism, polarity and parallelism. Parallelism means that Earth's axis, as you see in the diagram, is always parallel to itself at all positions throughout the orbit. In other words, if you look at the summer position, the fall, the winter, and the spring, the vernal, they're all the same angle, they're all parallel to each other. The axis is not flipping and flopping around like this. We don't have to scratch our head and wonder, I wonder what the angle is now. No, the angle stays the same. It's always parallel at all positions. That doesn't mean that it always has the same relationship to the sun. That's the thing that's going to give us our seasons. Because just to preview where we're headed, on the right, you see that same axis tilt points into the sun during the summer, leans in toward the sun like this. But in the winter, you take that same tilt, but then you put the Earth on the other side, and now it's leaning away from the sun in the northern hemisphere. So just by moving the Earth from one side of the orbit to the other, it changes the relationship between the axis and the sun. Whereas in one point, summer, it's leaning in, but the sun's in the middle, and the winter, it's leaning out over here. But it's always parallel to its position at all points. That's called parallelism. So those are our two properties. Polarity always points to the North Star, Polaris, and parallelism, that axis is always parallel to itself at all points in its orbit. Now let's take a look at the path that the Earth takes on its orbit. If we were to go into space, there's no actual surface or flat plane up there, but the Earth traces its orbit, so to speak, on an imaginary flat surface. When we see the orbit, and you can see it here too in this picture, the Earth is this blue third rock from the sun here going around. You can see that's a big ellipse there, and that ellipse is traced on an imaginary surface, just like Jupiter or Saturn or Uranus are traced on an imaginary surface. We could take a pizza box or a chessboard or something, and we could lie it down flat on those ellipses. And we have a name for that imaginary flat surface that we could sort of lay down there. It's called the ecliptic plane. And the ecliptic plane we have in gray here. Notice that it's kind of like a gray sheet, you might say. It's just like a flat surface that's imaginary. It cuts through the middle of the Earth, and then it cuts through the middle of the sun. Again, obviously, this diagram is completely off scale because the sun's much bigger than Earth. And we just draw it smaller in here so we can focus on the Earth. So that's called the ecliptic plane, also known as the plane of the ecliptic. It's the 2D plane that contains the Earth's orbit within 3D space. So in other words, the Earth orbiting, but it's not just orbiting in any old direction. It doesn't orbit this way and then orbit this way some other time. It stays on that 2D ecliptic plane. So that's going to help us to understand the tilt of that axis. What exactly is that tilt? So if we take that ecliptic plane, that flat surface, the plane of the ecliptic here, and we say, okay, here's that line, that flat surface going through the center of the Earth. And then we would take a 90-degree angle here, say this is a perpendicular to the ecliptic, right here, or take a T like that. And then we say, where's the Earth axis? Earth axis is always 23.5 degrees tilt away from the perpendicular to the plane of the ecliptic. Okay, so that's always a 23.5 degree angle right there, where the Earth's axis is away from 90-degree angle to the plane of the ecliptic. That's what the tilt is tilted from. That number is very important because 23.5 is going to give us the latitudes of the tropical circles, Tropic of Cancer, Tropic of Capricorn. And then 90 minus 23.5 is 66.5. And that's the number of our polar circles, Arctic and Antarctic circles. So we get everything from that tilt, all those numbers, 23.5, and then 90 minus 23.5 is 66.5. It's a very good number to remember. So all latitudes, if you look at the diagram, the equator, all these latitudes, all the parallels are all tilted at that 23.5 degree angle. So let's pause here for a second to say that these are basic principles that we've done so far that are going to be built on as we go forward. And none of the stuff that we're going to do later about the seasons and the insolation is going to make a lot of sense until we've got this first part down. So if you're not too sure about what we've done so far, I would loop back and do that a few times and make sure you're very solid on those ideas: the plane of the ecliptic, the Earth's rotation, the orbit, the shape of all that, and make sure you've got that, and then move on from there. Let's talk about the way that the sun hits the Earth. So the Earth at all times is always divided into a light and dark hemisphere, a sunlit hemisphere, the illuminated hemisphere, and then an unlit hemisphere, a darkened hemisphere on the other side, away from the sun. And there's a line between those two, which you can see on the Earth's surface, an edge where the lit, illuminated hemisphere becomes the darkened, unlit hemisphere. And that line has a name. It's called the circle of illumination. It's the edge where the illuminated hemisphere becomes the darkened hemisphere. It divides the light and dark hemispheres. You can't see that edge from the ground because it's too big, it's too fuzzy. But if it crosses over you, it means that night is coming or day is coming. So, for example, if we were to freeze the Earth, because remember, we know that normally the Earth is rotating around every day one time. But instead, if we were to make the Earth stop and let the light rotate around instead, so instead of the Earth rotating through the light, have the light rotate around the Earth like this, so we can see it this way, then you can see how the sun rises in the east and sets in the west. So if we're in Virginia right here, it's nighttime, sun's about to come up, and boom, it came from the east over here, right? The sun came in from the east. Let's do it again. So again, here's night falling. And notice that the sun is leaving you off to the west, right? The light went away to the west. That's why the sun sets in the west. So here comes the new sun from the east. And then it's daytime. And then here comes night. And look, there's the light part, right? The light's going to go away towards the west. Sun's setting in the west. Okay, so the sun rises in the east and sets in the west as the Earth each day rotates through the circle of illumination into the illuminated hemisphere and then rotates out of it into the darkened hemisphere every day. So let's look at the radiation itself now that comes from the sun. What exactly is coming at us from the sun? There's a word that's combined from three other words that they use for all of that radiation from the sun. It's called insolation, not insulation like a down jacket, but insolation. Incoming solar radiation. They take three parts of those three words and they put them together to make insolation. And it refers to more than heat and light because there's many different aspects of the spectrum of radiation. You have infrared, ultraviolet, microwaves, gamma rays, X-rays, plus heat and light coming out of the sun. All of that radiation together is called insolation. We get all of that from the sun. The difference between those is that they're on a spectrum, and some have shorter wavelengths and some have longer wavelengths as you go down. And the ones with shorter wavelengths are stronger because they can penetrate through clouds and other obstacles easier, whereas the longer wavelength radiation is weaker and it cannot penetrate as well. So one of the most important things to understand about what creates our temperature differences around the world is the sun angle, also known as the angle of insolation, the angle at which the rays from the sun hit a particular place on Earth. So it could be changing from season to season, just where you live. So if you live in Virginia, it might be high in the sky in the summer, like you see in the picture, a high sun angle. It's not going to be directly over your head because that only happens in the tropics, but it'll be pretty high in the summer. Whereas if you notice, if you look in the winter, it's not going to be very high. It's going to be a lower sun angle. And we can see that in this diagram here. In other words, the arc that the sun makes in the sky will actually get higher in the summertime, and then it'll get lower in the wintertime. So the sun will never rise too high up in the sky in the winter. So depending on when you're watching this, you know what season it is, look and see how high is the sun getting, somewhere around the middle of the day. And then maybe compare it later in the year. And it's going to be very different, say 3 months later. The sun's rays at any given time are only hitting at one point on the earth directly overhead, meaning at a 90-degree angle like this. We call these direct rays from the sun. The direct rays at a 90-degree angle are the most intense rays. And the place on Earth that at any particular moment is under those direct rays is called the subsolar point, because it's directly under the direct rays of the sun, the subsolar point. So in this diagram, you can see that the subsolar point is at the equator, but it doesn't stay at the equator. It migrates up and down, because we'll see that when the Earth moves around in its orbit, the angle changes compared to the sun. And so the direct rays sort of migrate up and down throughout the year. But we have to put it somewhere on this diagram. And so we put it right in the middle spot, which is at the equator. That means that the most direct, intense, strongest radiation from the sun is going to be concentrated there under those direct rays, somewhere around the equator at all times. It's always in the tropics. That's what the tropics are. They're defined as the area where the sun's direct rays hit. From 23.5 north is the highest, most northerly point they hit. 23.5 south is the most southerly point that the sun's direct rays will hit. So this is going to be our biggest areas of insolation, the most amount of radiation from the sun. By contrast, everything else gets some set of indirect rays, and they become more and more indirect the further you go away from the subsolar point. So down here in this area, the direct rays, here's the subsolar point right under the sun in the middle. But as you go away from that subsolar point, the rays only become more and more indirect. And that's because notice that the surface of the Earth, the curvature of the Earth, puts it at more of an angle to the sun. So where the incoming rays are not hitting flat, when you're up in Sweden, for example, they're hitting at an angle like this. Okay, so it's flatter and flatter like that. So it's indirect rays. And those indirect rays are weaker. The more indirect they are, the more weak they are, meaning the less energy you get if you're standing under those rays. And let's see why that is exactly. It's because if you look at the picture, it's actually very helpful because they have these three red lines of sun, of insolation. And it's actually useful because it shows you that the sun is not changing what it's shining. In other words, if we have 3 red lines worth of insolation coming in here, the sun didn't do something differently up in Sweden and Greenland up here in the north. It's the same sun coming in. There's no difference. It's not that. It's the Earth's angle of the Earth's surface that's making the difference. And what is the difference? Well, imagine if I had a flashlight and we turn out the lights in the room and have a flashlight, and then we have all the lights out, it's pitch black. Turn on the flashlight. Flashlight shines down on a table or on your hand, for example. What's it going to look like? It's going to be like a circle underneath of it, right? Pretty much like this picture at the bottom. Okay, it's going to be a flashlight shining down, and the rays are going to be concentrated in this area right here. So it's going to be hotter there. Smaller area, all the 3 red lines concentrated in a smaller area. 3 red lines worth of insolation, 1 small area. So if it's your hand or your arm, it's going to get warmer right there under the flashlight. But if I take that same flashlight and instead of shining it straight down like this, I go like that, and I shine it at an angle like this, what's it going to look like on your arm or on the table? It's going to be a longer shape like that, right? Like you see up in the top, these are the indirect rays, and they're stretched out over a larger area like this. But it's the same flashlight. Did we change the flashlight? Nope. Same flashlight, same amount of energy. 3 red lines. Nothing changed coming in. It's just the way that it hit that changed. But because now it hits over a larger area, everybody gets less because you have the same amount of energy spread out over a wider area. Just like if I have $100 and I give it to 3 people, they get a lot compared to if I give it to 30 people and then each one gets less. It's diluted, it's spread out over a wider area, wider amount of people. Okay, so that's why the sun's insolation is felt less up here. It's weaker in the northern latitudes the further you go away from the direct rays, from the subsolar point. More indirect the rays get, the weaker they get. That's very important to realize. That's why the northern and southern parts of the world, the 2 polar regions, are so cold, because it's so indirect up there that the incoming solar radiation is very weak compared to the tropics, which are your hottest areas of the world. So again, here is another good place to go back and review that middle section, because those are also necessary to understand the seasons that we're about to do coming up. Get real solid on those fundamentals, and then you can move to the seasons. So now we can put what we've got together and see how do we get our 4 seasons out of the Earth's orbit, rotation, orbit, and then the insolation coming in from the sun. So the 4 seasons are a result of the way that the Earth's tilt relates to the sun in the middle of the orbit at different times of the year. So basically, the first day of the summer is called the solstice. The first day of winter is called the winter solstice. The first day of spring is called the vernal equinox. And the first day of fall is called the autumnal equinox. So these are the first days of each of the seasons. The equinoxes are our moderate seasons, where we have spring and fall. And then the solstices are the first day of our extreme seasons, where we have summer and winter. These dates on here are not specific. They are for a particular year. It shifts a little bit depending on the year. So these are not always the same dates. It changes a bit. We can see that during the summer, our axis is leaning in toward the sun. So just imagine, like, if your head is the Earth and the sun's out in front of you, then you head to the axis like this, you're leaning in like that. Well, what's going to happen to that radiation coming at you from the sun? It's going to sort of climb up your face, right? If you're facing the sun out there and then you lean into the sun more, then the subsolar point, right, would normally be here. Let's say if you're flat, but then if you're leaning in, it's climbing up like that without the sun doing anything differently. It's just that you're leaning into it, so it's climbing up your nose and your forehead up to the ear, right? So the subsolar point climbs up the surface of the Earth during the summer to where instead of at the equator, it's more like up here at the Tropic of Cancer during the summertime at the summer solstice. That's the definition of the summer solstice. It's when the sun's subsolar point, the direct rays, hit at the Tropic of Cancer, the highest point that they'll get. And then at the opposite season, winter, the sun's rays, this time it's like you're leaning your head back, right? So now the sun's rays are going to get lower and lower on your face to where they hit down here. So instead of the sun hitting at the equator, it's going to hit somewhere in the southern hemisphere, the direct rays. The subsolar point will be at 23.5 south, the Tropic of Capricorn. That's the southernmost place the sun's direct rays will hit. So that's the trip, so to speak, that the direct rays make. They go up to 23.5 in the summer, that's as far as they get. summer solstice, and they come back down and pass over the equator and go to 23.5 south, Tropic of Capricorn, and they do it again throughout the year. So the difference between summer and winter is that where axis is leaning in the northern hemisphere and leaning out in the northern hemisphere, and the opposite is true in the southern hemisphere. So let's look closer at summer. What exactly happens and changes during the summer when we lean in to that sun? Well, a series of byproducts come from that. One is that when you lean into the sun, and I put a star here where Virginia is, then it makes your days longer. Because if you remember, we said that the Earth rotates from west to east, right? From west to east or from left to right on the map. So here's Virginia right here, this star. And we can just take a line, let's say it's approximately like right here, and rotating from west to east every day. But look, when you're at this angle, here's our circle of illumination right here. Our axis is not lined up with the circle of illumination. Because remember, we said the circle of illumination splits the world in half light, half dark. But it's not lined up with that. The axis is not lined up with the circle of illumination. So it's not going to be half and half, light and dark. It's leaning into the lit half. Can you see that? Right? Virginia here, the northern hemisphere is leaning in. The southern hemisphere is leaning into the darkened half. So what that means is that as you rotate each day, you're going to spend more time in your day, more hours and minutes of your day, rotating through the lit hemisphere here because you're leaning into it, and fewer hours in your day rotating through the darkened hemisphere over here. And in fact, the spatial ratio of distance that you travel as you rotate more through this longer distance to the lit hemisphere here versus this shorter distance here in the darkened hemisphere is the same ratio as the number of hours and minutes that you spend in a day during daytime with daylight versus the number of hours and minutes of darkness each day. So you might have a lopsided day where it's 14 hours of light and only 10 hours of darkness, because the ratio of this distance here will be 14 to 10 between the distance through the illuminated part of the hemisphere and the distance through the darkened part of the hemisphere. And all that is because that imbalance is because you're leaning the axis, leaning the northern hemisphere into the sunlit hemisphere over here. And so that's the reason we have longer days up here, longer days, which give us more insolation. That just makes it warmer because the sun is out longer. It just stays out longer. The second thing that goes along with that in the summer, besides longer days, you have stronger insolation coming in, meaning that the intensity of the rays is stronger, not just the amount of time that it's daylight. There's more daylight, but it's also stronger sun during that daylight. And that's because the sun angle is higher in the sky. As we said, you're leaning in towards the sun, and so the sun is going to be higher in its arc through the sky during that summer, and that's going to be more direct. There'll be more direct rays coming on you. So in the summer, you have more direct rays, you have stronger sun, and also longer sun because you're spending more of your time spinning through the sunlit hemisphere and less of your time spinning through the darkened hemisphere. In the wintertime, it's exactly the same, except in reverse. Now you're spending more time rotating through the darkened hemisphere because the axis is now leaning out leaning into the darkened hemisphere more. It's not lined up with the circle of illumination. And hence you'll spend more time rotating through darkness each day, and that will give you more hours of night each day, and your days will be shorter than your nights. And the opposite is same as true with the strength of the insolation. Now that you're leaning away from the sun's angle will be lower in the sky. You have a lower sun angle, and therefore you have weaker insolation, weaker sun coming in. So wintertime, shorter days and weaker sun, all of which makes for colder weather. And like we said, the first days of those extreme seasons, summer and winter, are called the solstices. You think solstices are the extremes. It's the longest and shortest days of the year. It's just the first day of summer and the first day of winter. So the first day of summer is the longest day of the year, meaning longest daylight. The first day of winter is the shortest day of the year, the shortest amount of daylight, the longest nighttime. The two solstices. But there are also two equinoxes. Equinoxes, it comes from the Latin nox, meaning night. And so equal night. It means that in the spring and the fall, which are referred to as vernal and autumnal on this diagram, the equinoxes are the first day of spring and fall when you don't have any difference between daylight and night. It's the same 12-hour days, 12-hour daylight, and 12-hour of night everywhere in the world, not just in some places, but everywhere in the world. That's what the equinox is. On the first day of spring and the first day of fall, you have 12-hour days and 12-hour nights everywhere in the world. So let's look and see why would that be exactly, based on what we've been talking about. We said that in the summer, the axis for the northern hemisphere, for example, in Virginia, is leaning in, not lined up with the circle of illumination, but leaning into the lit part. And in the winter, it's the opposite. It's not lining up with the circle of illumination. The axis is leaning into the darkened hemisphere. What about during fall and spring? Where is it leaning? Is it leaning into the darkness, leaning into the light? And the answer is, it's not leaning into either of them. It's actually in the fall and spring equinoxes, first day of fall and spring, the axis is lined up with the circle of illumination, straight with it, just like this. Here's a circle of illumination. Here's the axis right with it. So hence, the axis of the Earth splits right through the day and the night, the lit and the darkness. So everybody in the world gets 12-hour days and 12-hour nights. There's no difference in the daylight versus night among anywhere in the world on the equinoxes. Hence the name equal night, that night is equal to day, equinox. And in case you're wondering, what about the Earth's axis? Where is it pointing? It's a good question, because we said it's pointing in toward the sun during the summer, but it's pointing away from the sun, leading out during the winter. Where is it pointing during the equinoxes, fall and spring? It's not pointing in toward the sun. It's not leaning in toward the sun like this. It's not leaning away from the sun like this either. It's actually leaning off to the side like this. Okay, it's leaning off to the side, which doesn't put it into or out of the sunlit or darkened hemisphere. So it's the axis is off to the side, but lined up directly with the circle of illumination. The equator is like a permanent equinox. Every single day at the equator is 12-hour days and 12-hour nights. So let's look at a little bit of the cultural aspects of how these equinoxes and solstices affect human beings. Humans have known about the equinoxes and the solstices for thousands of years. They've been aware of these. using the equinoxes and solstices as milestones or key points throughout the year. So, for example, you have the equinoxes, the first day of spring and the first day of fall, are traditionally the times when cultures plant or harvest their crops. For example, at the first full moon after the fall equinox is harvest moon. It's considered to be the harvest moon. It's about that time that they have Oktoberfest in Germany, in Bavaria. And this is the time when you harvest all your crops, you bring them all in, and they celebrate. They have lots of beer, lots of drinking, lots of food, lots of sausages, because they're celebrating all the end of the work that they've been doing to harvest all their crops. And they're settling in for the winter, where they're going to go a long period just living off of what they've stored for the winter. And in Mexico, in the Mayan region of Yucatan, which is this peninsula hanging off of Mexico down here, in the place called Chichen Itza, there's a famous temple of the serpent at Kukulkan. And you see in the picture, this temple is designed ingeniously to be a sort of alarm clock for the fall and spring equinoxes. They engineered this temple so that only at those two moments in the year, only at the fall and spring equinox, does the shadow, see this undulating shadow that you see, the wave going down, that only shows up as the body of this snake at those exact two times in the year. Most of the year, you don't see this shadow. But only when the sun hits on those 2 days does it hit the corner here of the temple, which then casts the shadow of the snake to connect the body with the head that's always there waiting throughout the year. So the fall and spring equinoxes are marked or announced by the appearance of the full snake on the Temple of Kukulkan twice a year. And you can see tourists go to see it and to capture it on film every year at those two times. So now that we've seen the seasons, the two solstices, the two equinoxes, the first day of summer and winter, and the first day of spring and fall, let's take a look at what the sun's rays are doing from space. So here's the sun, and here's our vertical rays or direct rays, and the point underneath is called the subsolar point. And so we said that in the summertime, right, when we've leaned in as much as we're going to lean in, the summer solstice, that is the point when the direct rays are right over the Tropic of Cancer, 23.5 north. That's what it is. That's why the Tropic of Cancer is there. It's because it's the highest point, meaning the most northerly point, that the sun's direct rays will hit. And so the Tropic of Cancer becomes our subsolar point on the summer solstice. And the inverse is also true. During the winter, our subsolar point is the Tropic of Capricorn down here, 23.5 south. So it's summer in Australia, in South America, in South Africa, places like that. So the subsolar point, well, under the direct rays, migrates from 23.5 north at its northernmost point all the way down to 23.5 south at its southernmost point, and then comes back for the summer again, and then back again during the winter. It keeps doing that all year long. In other words, the subsolar point is always in motion. It never stays in one place. That's why we said earlier that when we had the diagram that showed the subsolar point at the equator, it doesn't always stay at the equator. And this is showing you that here, because it's showing you the northernmost point that it moves to is the Tropic of Cancer, and the southernmost point, the Tropic of Capricorn. That means that if you are anywhere in between those 2 points, you are in the tropics, they say, right between the Tropic of Cancer and the Tropic of Capricorn, all the space in between them is called the tropics, then everyone in the tropics gets passed over by the sun's direct rays twice throughout the year, once on the way down and once on the way back, like this. So, for example, the equator or Hawaii or someplace in the tropics, it passed over once and then passed over twice. A place like Virginia would never be passed over at all because it's not between 23.5 north and south. It's not in the tropics. So the direct rays are right over every place in the world in the tropics twice per year, but they only hit the Tropic of Cancer. The direct rays only hit the Tropic of Cancer one time per year, and then it's another 365 days before they come back. And they only hit the Tropic of Capricorn one time per year too. So just to visualize it, this map is showing you the area that we call the tropics. It's the region between the Tropic of Cancer, 23.5 north, and the Tropic of Capricorn, 23.5 south. So these tropics are the only places in the world that are ever going to get your direct rays at some point in the year. So if those are the tropics, the places where the sun's direct rays hit, then generally speaking, they say the world is divided up into three basic sort of types of latitudes: the tropics, the middle latitudes or mid latitudes, and then the polar latitudes up top. We'll come back to that later when we look at climates. But what's different about the mid latitudes? Well, the tropics are going to be very hot because they're at some point, everybody in there is going to be under the sun's direct rays. But the mid latitudes never will be under the sun's direct rays. But that doesn't mean they're not going to be hot, because what starts in the tropics doesn't always stay in the tropics. We'll see that nature, sort of like an artist, has hands that it uses, which are, for example, the winds, global winds, and the global ocean currents. It uses to move temperatures away from where they start. So we're going to get those tropical hot air masses from this area in the middle, going to blow their way up and wash their way up in the ocean currents, the heat from that into the mid latitudes. But at the same time, the same thing is going to happen the other way, because they have such indirect rays in the polar latitudes. That cold polar air is also going to blow out and wash out in the ocean currents. And so you're going to have this meeting in the middle, in the mid latitudes, between warm tropical air in oceans and cold polar air in oceans. And that's why we have 4 distinct seasons in the middle latitudes, because we're the meeting place for tropical and polar air. And those two things meet and they converge and give us a lot of storms, okay, because we have contrasting air masses creating fronts. And they give us variable seasons, where in the summertime it's more dominated by tropical air masses, and the wintertime is dominated by polar air masses. So it's a big point to realize that the middle latitudes, they are the latitudes with the most variable weather in the world. And finally, up with the polar latitudes, they have the most indirect rays of all. So they're going to be the coldest of all. And it's like a near permanent winter up there beyond the Arctic Circle, 66.5. For example, if you look at Greenland here, the world's largest island, and 80% of it is covered in a giant sheet of ice, which is multiple kilometers thick. So last but not least, let's look at some special cases, some special situations that happen when you get very, very far away from the direct rays, very far from the subsolar point. You're talking about extremely indirect rays up there inside the polar circle, 66.5 north, and then below 66.5 south. So we're going to be talking about areas that are inside this red circle, the Arctic Circle. And by that, by inside, we mean from there all the way up to the North Pole. So kind of this cap on the top of the world up here, so to speak, like a hat. And then everything inside of the Antarctic Circle all the way to the South Pole, all this area. There's some special situations that happen only in here. And the special situations are we call midnight sun and polar night. Midnight sun and polar night. They're the upside down or inverse versions of each other. These are two phenomena which both happen in the areas that we've talked about. They happen inside of this red circle and inside of this red circle, the Antarctic Circle. Midnight sun is when the sun never goes down, meaning for 24 hours a day, you can still see the sun out there on the horizon. It never goes over the horizon and sets. Polar night is the opposite. It's when the sun never comes up. When you go 24 hours and the sun never comes up, it stays over the horizon. So here's an example of midnight sun up in Norway. And this sun will never go down during the day. Now, it's not going to go very high in the sky because you're so indirect up there, right? Remember, over your head directly would be only in the tropics. So it's always going to be very low in the sky, but it never sets during these times of the year. This would be the summertime in Tromsø, Norway. The sun will never set. It'll just hover on the horizon. But you may ask, well, does it move at all? Because usually the sun goes up and it comes down and it rises in the east and sets in the west. So where is it moving here? It does move, and it might move up and down a little bit, but not that much. But the bigger movement is going to be rotating around you, because really what's happening is you're leaning into the sun and then you're rotating under it because the earth is spinning. So you're under the sun and then you're rotating around like this, like a merry-go-round, sort of at an angle, a merry-go-round at an angle. So what it's going to do is, imagine we're taking this picture. Imagine you have the camera. You got the camera in your hand and you're in a house. Okay. And that house has the front door with a little porch in the front, and you're sitting on that porch. So you're sitting on the front porch of the door of your house facing that sun. That's where your lake house looks like in Norway, or your fjord house, whatever that might be. And so what will happen is that the sun may not go very high in the sky, but 12 hours later, it's not going to set. It's going to be at your back door, right? So you're sitting on your front door on the porch. The sun will rotate around you circularly to the back side. And so if you were to get up and move to your back door, open up the screen door and go to your back porch, you could take a picture and the sun would now be on the other side of your house. So it won't rise and set. It will just rotate around to the back of your house. That's what happens to the sun during the midnight sun, the times of the year when the sun never goes down. And again, that only happens in latitudes that are beyond, they're at this red circle, the Arctic Circle, and then beyond it. So where was Tromsø, Norway? That's way up here's Norway. It's the top of Norway. It's one of the very northernmost parts of Norway. If you're wondering where it is, Google Tromsø, Norway, and you'll see how high it is. It's way up there. That's midnight sun. The sun never goes down. And to be clear, that happens for a increased number of days the further you go up towards the North Pole. So in other words, at the Arctic Circle itself, this red line, or the Antarctic Circle, this line down here, if you're on it exactly on the circle, you'll get 1 day per year in which their sun never goes down, of midnight sun. But as you climb up the surface of the earth from here further and further towards the pole, North Pole or South Pole down here, then the number of days in the year that have the sun never go down, midnight sun, will keep adding up and getting more and more and more. We'll come back to that in just a moment. Here's the other phenomenon, polar night. It's the opposite of midnight sun. Midnight sun was when the sun never goes down. This is when the sun never comes up. Now, I could just have a picture of blackness where you can't see anything, but here you put a picture of something called the blue hour, which is the time of the day when at least there's some natural light in that same city of Tromsø, Norway. And where's the light coming from if the sun ever comes up during this time of the year, polar night? It's coming from the twilight over the horizon, just like before the sun comes up in the morning, you have pre-dawn twilight, and then after the sunset at night, you have that glow you can still see for a while. It's that. It's called the blue hour. And this is the time when, if you have things to do in Tromsø, this might be like 4 or 5 hours of the day where you have natural light, and you would take advantage of that to run your errands and do your thing. If the sun never comes up during the day, there might be just a little window in the middle of the day when you could have this blue hour. So to wrap this up and see the big picture, at the Arctic or Antarctic Circle, the midnight sun or polar night phenomenon, midnight sun in the summer, polar night in the winter, are only going to be 1 day per year at 66.5. But as you climb up further towards 90 degrees north or south, the number of days per year where the sun never goes down or never comes up increases. How much does it increase? Can it keep on increasing forever? Well, it's mind-blowing to think that once you get to the North Pole or the South Pole, the number of days that the sun never goes down or never comes up, polar night and midnight sun, is all of them. In other words, the entire year. In other words, when you get to the North Pole, then for half of the year, it's daytime. Half of the year straight, the sun never goes down. The other half of the year, the sun never comes up. So basically, at the North and South Poles, they have 1 day per year. Half of the year is light, sun never goes down. Half of the year, sun never comes up. That'd be a pretty strange place to live. But that's what they have. And so the number of hours of daylight to night, the ratio at the poles is always 24 to 0. 24 to 0. And right in the middle of the year, it splits and it changes over from always up all day long, the sun, to always down after that for the second half of the year. So it's pretty wild. They have 1 day per year at the poles. Whereas, as we said, it's the opposite at the equator down here. Instead of a complete imbalance of 24 hours of either dark or light, you have 12 and 12 every single day at the equator, a permanent equinox, you might say. And in the middle latitudes, you have, for example, it might be 14.5 hours of day and 9.5 hours of night in Washington, D.C., or vice versa if it's the wintertime, something like that, a lopsided day and night. It gets more lopsided the more you go towards the poles. So that's a look at Earth and Sun relations. We saw how the Earth moves in an orbit and rotates relative to the Sun. We saw how the Earth axis is positioned relative to the Sun, depending on where it is in that orbit. And we saw how that all changes the angle of insolation coming from the Sun, which determines how strong the insolation is or weak, which gives us very big temperature differences on Earth and helps to determine our seasons, which then have major influences on the cultures that humans have all around the world.